Welcome to dilution problem solving. In this video, we will look at the process of dilution and the origin of the mathematical relationship for dilutions, and then work through 3 practice problems. So this drawing shows an important feature of the dilution process. If you count the yellow little solute molecules, you'll see that they are the same in the concentrated version on the left as they are in the more dilute version on the right. All we've done is add more solvent, more of the blue, so that the molecules are less concentrated and there's more space between them. So hold on to the thought that the number of molecules or the number of moles of the solute stays constant during a dilution process. So we'll take a look at this example in what will be probably gory detail, just to kind of see how the process works, what's changing at each step along the way. So if 10.0 milliliters of a 0.10 molar copper sulfate solution is diluted to 50.0 milliliters, what is the new concentration of copper sulfate? Right? Well, you know already it's going to be smaller. We're diluting it. We're sort of watering down our solution, so we know what we're expecting. But let's work through the numbers. So we'll start with our big jug of stock solution. This is a pretty typical process in a lab. Will be much easier to make a huge amount of a concentrated solution and then dilute it as you need it to go along, rather than constantly making new solutions. So we'll start with the concentration, the molarity of our stock solution, 0.10 moles per liter. And the volume is 3 liters. So how many moles of copper sulfate are in our original container there? Well, we can do the math, and there are 0.30 moles. But we obviously don't need such a big container. So we're going to move to our next step, which is to scoop out. Obviously, we'd be using something more accurate than a teaspoon, but let's say we're going to scoop out 10.0 milliliters sample of this. Okay? So the concentration is the same, right? That's an intensive property of the solution. It's homogeneous. It's the same all throughout, the concentration. But our volume is much, much, much smaller, right? So our number of moles, when we calculate it, is much smaller in our tiny little sample in our spoon. We have 1.0 times 10 to the minus 3 moles of our copper sulfate contained inside that 10 milliliters. Well, in order to dilute it, we need to put it in a bigger container. So that's our next step, is to put our 10 milliliters into a much larger container. So let's think about it. What's the concentration and the volume in our new container? Well, we haven't done anything to it. All we've done is put it in a larger bucket. So our molarity and our volume are the same, which means, of course, that the number of moles is the same. Again, we haven't done anything to our solution. We've just moved its location. Okay? The last step, we're going to actually do something to our solution. We're going to add more solvent, in this case water, up to that dilution, up to that volume mark on our 50 milliliter flask there. So we're going to add some more solvent and then, of course, mix. But what hasn't changed? The number of moles of solute. We have not added any more copper sulfate to this. We're just going to add some solvent. So once we do that, our new volume will be 50 milliliters, or 0.0500 liters. And now we can calculate our new molarity, 0.020 moles per liter. As expected, less than the 3 moles per liter, or the 0.10 moles per liter that we started with. Well, that was a lot of work, wasn't it? Let's condense down all of what we just talked about into a shorthand version. But before we do that, I have to give you this warning that this nice little relationship, which is extremely seductive, you're going to want to use it for lots of things, is only for dilutions. So promise yourself right now that you will only use this relationship for dilutions. All right, so after all of our calculations in the previous chart, we can boil this down to a very shorthand version here. We have our initial set of conditions, our initial concentration and volume, and our final, or our diluted version over here, molarity and volume. they're both equal to the moles of the solute here in the middle. So if we remove that part and put those two ends equal to each other, you have MIVI equals MFVF for initial and final. Some places show it as M1V1 equals M2V2, definitely easier to say. But again, it's a set of two conditions, one at the beginning and the second at the end. Or the last one, which is the one that I like to use, which is MCVC for the concentrated version, your starting amount that's more concentrated, equals MDVD for the diluted version, sort of the ending point of that. It helps me to kind of focus on getting the information out of the problem and correctly identifying what goes where. All right, now we're ready to actually apply this relationship and see how this works in a real problem. Here's our problem. What is the concentration of calcium chloride if 3.5 milliliters of 0.444 molar solution is diluted to 675 milliliters? I like to ask myself 3 questions before we get going. So now we'll ask them each time just to make sure that we're doing things properly and we're not using that relationship if we can't. So we'll ask myself, is this a dilution problem? Well, the word diluted is in the problem and that kind of gives it away. So yes, it is a dilution problem. So yes, we can use our nice simple relationship that we just saw in the previous slides. Can you identify 3 of the 4 variables in that relationship? Remember, there were 4 things in there. If we know 3 of them, we can find the missing 4th one. So the answer to that is yes. Here are some tips for getting information out of the word problem. That word of is an important little word. It connects the volume, 3.5 milliliters of, to the concentration, 0.444 molar. Those 2 bits of information go together. They are for one of those solutions, either the concentrated or the dilute one. And the story of the problem tells us that this 3.5 milliliters of this solution is diluted. That tells me that this information circled in red is the concentrated information. So I can make a little table of that and put that off to the sides, kind of organize my information for myself. Now I can use my handy dandy little relationship here, MCVC equals MDVD. You can substitute in my information now that I've pulled it out of the story problem. And now I have to do some algebra. So again, make sure you're up to date on your algebra. Practice these problems so you'll get good at it. And our final diluted molarity is 0.0023 moles per liter. Does that make sense? It should be less than what we started with, and it definitely is. And it should be less by a lot. If you notice, the volume change was quite a significant volume change, so we should expect quite a significant decrease in the molarity. And one more thing to point out is that you can use any volume unit in this relationship. We did not have to change these into liters like we do when we're doing dimensional analysis. We can use any volume unit as long as it's the same on both sides. So we could leave this problem in milliliters. We could change both sides into cubic feet if we were so inclined, but we opted for the easy version, which is to leave the units as they were and just check that they match each other. All right, let's get ready to try another one. Remember to pause the video if you want to try this on your own before you watch the solutions there. All right, number 2. What is the concentration of calcium chloride if 16 milliliters of 3.0 molar solution is diluted to 500.0 milliliters? Okay, again, remember, ask yourself these 3 questions before you get going so you know that you're allowed to use our nice dilution relationship. So yes, it is a dilution problem. This problem sounds a lot like the one we just did. It has the word diluted in it. So of course we can use our simple relationship. And can we identify 3 of the 4 variables in this relationship? Again, yes. It's got that magic word of in there, so we know that 16 milliliters goes with 3 molar. And that solution is diluted. Right? So that's the solution that's going to be diluted. It's the one that's concentrated already. And it's diluted to 500.0 milliliters. So again, we can summarize all that information before we get started. just to make sure that we have it all. And then we can write down our relationship, and now it's a matter of solving this problem algebraically. We can substitute in our values that we identified from the problem, do our algebra, and get that our new diluted molarity is 0.096 moles per liter, or 0.096 molar solution. Again, note that we did not have to change the volume units at all. They were already matching, and we did not have to change them into liters. As long as they were the same, we can go ahead and use them as is. All right, now on to the third one. This one's going to sound a little bit different. How many milliliters of a 3 molar calcium chloride solution do you need to make 500.0 milliliters of 0.850 moles per liter solution? This one definitely sounds different. It doesn't have the word diluted in there. So you have to read it and think about what is going on in the problem. Let's kind of make a little movie in your head of what's going on there. You're starting with a bottle that says 3.0 moles per liter on it, and you're trying to make a certain volume, 500 milliliters, of a lesser molarity. Note that the molarity went from 3 to 8.850. That's a dilution. It's gotten less concentrated. So yes, it is a dilution problem. And yes, we can use our same relationship. What's different here is the pieces of information that we have. We do have 3 of the 4 variables identified here. So again, that word of is connecting our 500 milliliters to the 0.850 molar solution. That's where we're going to end up. It's connecting my volume and concentration of the dilute solution. Okay, those two go together. So those are my molarity and volume of the dilute solution. So those are together here. So it's a little different from last time. And we know the concentration of our initial amount. So there's our relationship again. We'll substitute in the values that we identified in our problem, solve for the algebra, and get that our concentrated volume is 140 milliliters. So to kind of answer the question in words, if we took 140 milliliters of 3.0 molar calcium chloride solution and took that little sample and diluted it, added enough solvent to make 500 milliliters, our new concentration would be that diluted concentration we were aiming for, 0.850 moles per liter. As a little side note, you could also use any concentration unit, as long as, again, it has to be the same on both sides, and it uses volume of solution in the denominator. So some concentration units don't use volume in the denominator, but since both of these are molarity and they both use volume in the denominator, the liters of solution, we can use that unit. So thank you for joining me for dilution problem solving. See you soon.